Hi, I am François Darmon, presenting our paper Learning to Guide Local Feature Matches. In this paper, we propose a new guided matching approach that improves traditional keypoint matching. Traditional SIFT matching is known to fail in challenging conditions like here, where the texture and lighting are very different. But suppose we have access to coarse matches. Those matches can define, in both images, small regions that match. Keypoint matching would be made easier since there is less ambiguity. We propose to use a deep learning-based coarse matching step that produces such regions. We can now match keypoints inside the small regions based on the descriptor distance. Our approach improves SIFT to the level of recent learned features. Since the adoption of SIFT, most work has focused on learning better local features, either feature extractors, feature descriptors, or both at the same time. Recently, many papers try to do this task with a learned approach. Orthogonal to these works, improvements can be made on the matching stage. Developing a guided matching approach seems very natural, but since it requires an accurate initial step, most approaches fail at providing better matches. Our approach is the first to do guided matching with deep learning. The coarse matching network takes as input two images and outputs low-resolution matches. It is composed of a shared feature extractor for both images. The features are compared via dot product into a 4D correlation volume. This volume encodes every possible comparisons between each locations of the two images. It is further processed by 4D convolutions. In the end, output matches correspond to maxima in the processed 4D volume. We investigate three types of network supervision. First, image level supervision. It is the weakest form of supervision. We only need positive pairs and negative pairs. Positive pairs are pairs of images with a significant overlap, and negative pairs are pairs from different scenes. The loss enforces the matches of positive pairs to be sharp maxima, and maxima from matches of negative pairs to be flat. Second, we introduce epipolar supervision. It is a weak supervision since the only information comes from the relative pose between images. The loss encourages matches consistent with epipolar geometry to be sharp maxima of the coarse volume. It also penalizes sharp maxima when the corresponding match is too far from the epipolar line. Finally, point supervision. It is the strongest form of supervision we study. It uses ground truth matches from a SFM model. The loss enforces sharp maxima on the matches that correspond to a ground truth point. We could add a penalization of negative matches, but it is hard to define, and our experiments show that the best results are obtained with this loss formulation. We now evaluate quantitatively our matching method. We first perform a direct evaluation of our coarse matching network. Then, we evaluate the matches on 3D tasks that uses the matches as input, namely visual localization, two-view geometry estimation, and structure from motion. First, we evaluate the coarse matching stage alone. We use Megadepth's ground truth SFM, and we count the number of ground truth points correctly predicted by the coarse matching. The three supervisions are compared in this table. Although it is not the strongest form of supervision, epipolar supervision performs the best. It may be because point supervision is biased, providing information only on parts that could be reconstructed by SFM. Then, we evaluate the quality of feature matching using our method. We use the match for visual localization on Aaron day night. This dataset consists of a set of daytime images with known poses and queried nighttime images. The task is to find the pose for the query images. We use our matching technique to match different local feature methods. Apart from D2Net, that is current state of the art, our matching improves the accuracy of the raw features. Here are qualitative examples of day-night matching in this dataset. Note how challenging these image pairs are, where both lighting and viewpoint vary. In this setup, SIFT matches are not good enough for visual localization. After the outlier filtering, the remaining matches seems random. But using our guided matching technique, SIFT features can now produce much better matches. We also evaluate the matches for two-view geometry estimation. We choose the same setup as OANet. We evaluate on two datasets, a subset of YFCC, Internet Collected Outdoor Images, and a subset of Sun3D, indoor images. The matches are used for essential matrix estimation, then it is decomposed into a relative pose. The metrics are localization precision at several thresholds. The results are reported here. First, we note again that epipolar supervisions leads to the best results. Here we study various traditional matching methods for SIFT, including ratio test and bidirectional tests. As noted in many papers, ratio test and bidirectional test are essential for matching SIFTs. Our matching improves all these traditional matching methods. Our method is comparable with recent approaches that learn outlier filtering from noisy matches. OANet is state-of-the-art on this table, and our method ranks second. Finally, we perform SFM from historical data. We report the average proportion of images successfully registered. We manually check that the reconstructions are not degenerate. On this task, using our matching allows to register more images into the model for every feature we tried. We also show qualitative results. Again, raw SIFT matches have low quality, but guiding SIFT features with our method works. In this paper, we introduce a new guided matching technique. Unlike previous method, it is able to improve SIFT matching in difficult settings. Our approach can be used with any feature method, and it can improve the results of recent learned features. You may find more information and detailed results in the paper. Thank you for watching.